In my first video on combinatorics, I said that I would try to be careful when I use the word combination. And the reason why was because in English, we use the word combination in a way that doesn't necessarily match up with the way it's defined mathematically. And since we're talking about combinatorics, the mathematical definition matters. This video will focus on permutations, but permutations and combinations are related things, but they're different things, and so I want to talk about what those differences are. So an ordered arrangement of objects from a set is a permutation. An unordered arrangement of objects from a set is a combination. So what does that really mean? Well, let's say I have three friends in this set. We have Alice, Bart, and Charles. And we'll just represent these as A, B, and C. And let's say I want to pick two of these three friends to help me out with something. So I might say, okay, I want Alice and Bart to help me. But I might say I want Bart and Alice to help me. Or Alice and Charles, or Charles and Alice, or finally Bart and Charles, or Charles and Bart. If I'm just picking two people to help me and it doesn't really matter the order that I picked them, then this is a combination, that's a combination, and that's a combination, right? Because I'm just saying Alice and Bart, Bart or Alice. I'm just picking two of the three people, right? So we have three combinations here. But what if order matters? What if I say, okay, the first person I call will do task 1 for me, and the second person I call will do task 2. Well, then these are two different arrangements, right? Because Alice is doing task 1 here, but Bart is doing task 1 in the second ordering. So these are two different permutations. So we actually have 6 permutations. So once again, there's only 3 combinations here, but there's 6 permutations, right? And in fact, if I was picking all 3 people, there really is only one combination because ABC and ACB and ACB and CAB are all the same. But there would be 3 times 2 times 1 equals 6 permutations in that case. So how do you keep it straight which one's which? What helps me is a memory aid that I saw many years ago, and that is combination locks should really be called permutation locks. In combination locks, you're given 3 numbers typically. So it might be something like this. It might be 32 right, 32 right, followed by 14 left, followed by 21 right. Well, that's clearly different than 21 right, 32 left, 14 right. If these were truly combinations, then whether I did the 32, 14, 21, or the 21, 32, 14, or any of the other 4 possibilities wouldn't matter. But order does matter, so they're really permutations of the values. Okay? So let's see how we're going to do this. We can't always produce all the arrangements. So what's the mathematical formula that we're going to use? So let's write the formula and then I'll explain it first. So one of several ways to write it is like this. P of nr is equal to n factorial divided by n minus r factorial, where 0 is less than or equal to r, less than or equal to n. Now alternative representations are, some people will have p with the n and the r here, where these will be actual numbers, and some will write p with the n and the r here, but this is probably the most common one. So how do we use this? So the number of permutations of r distinct, and there's actually no n here, distinct objects from a set of n objects. Sorry. Is this the number of permutations? So we'd say R distinct objects from a set of n distinct objects is the number of permutations. Okay? By distinct, though, in this case, no repetitions. Okay, and what do we mean by that? Well, let's use an example. Let's say I have some wooden blocks. So I have 26 blocks, each with a different letter. So there's 26 letters in the English alphabet. Each of these blocks has one of those letters. So how many three block words can I choose? And this is talking about permutations. Well, if we use the multiplication principle, which we talked about in my first video, I would say, okay, there's 26 values to choose for the first block, and so maybe I pick like the letter D, and that's here. So this is my block, letter D. And what do I have next? Well, now I pick one of the other 25 letters, so maybe I get Q here, and finally I have 24 others to choose from, so maybe I get T here. So these are nonsense words, but we're just talking about all the different permutations. So this right here is equal to 15,600. Right? There's no repeats here. I pick a block and I keep it. Now, if we said that I'm going to pick a block and then put it back in the stack and pick another one, so things like A are possible, not physically because I still only have one A, but if I pick an A, put it back, pick another A, put it back, pick another A, well, now we just have 26 times 26 times 26 here, which happens to be 17,576. Okay? So if we were going to do this, then somebody would say permutations with repetitions. Okay? But if you just say how many permutations, then you're talking about no repeats. Okay? So we don't reuse something unless it was part of the set. Now, if I had two A's already in the set, then it'd be possible to get two A's and still just consider that a normal permutation. How would the formula work for this, though? Well, our formula says, so we have 26 blocks to choose from, and we're through choosing 3. So I reach in, I grab 1, I grab 2, I grab a third. We have this right here. So this is 26 factorial divided by 26 minus 3 factorial, which is equal to 26 factorial divided by 23 factorial, which is equal to 15,600. All right. So note that if you're doing these, now modern day calculators may be able to handle this, but historically this would have been too much because 26 factorial is a huge number, and even 23 factorial would be huge. So you would have wanted to simplify. How do we get the same value each time? Well, how's this working? Well, 26 factorial is equal to 26 times 25 times 24 times 23 times 22 dot 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 all the way down to 1, right? Well, this part here, the 23 times 22 times 21 all the way down to 1, that's really just 23 factorial. So that means what we wrote here is 26 times 25 times 24 times 23 factorial divided by 23 factorial. Well, these cancel out, which means all we have left really is 26 times 25 times 24. Okay? Let's look at another example. So let's say in my closet I have 3 shirts and 2 pairs of pants. And so we're going to call these A, B, and C. And we'll call these X and Y. How many different permutations are there for hanging up these 5 things if I don't care about where they are relative to each other? That is, I can have a shirt, 2 pairs of pants, 2 more shirts, or I could have a pair of pants, 3 shirts, a pair of pants, whatever. Well, this is one of those cases where I look at it and I would use the addition principle, which I talked about in my first video, to say, well, I really have 5 clothing items, right, or 5 items. So what do we have? I can think then of having 5 slots on my rack to hang up things. So in my first slot, I can choose any of the 5 things, right? I have a shirt, a pair of pants, a different shirt, whatever. For each of these, I have 4 other things I can hang up. For each of those, I have 3 things, and so forth. All right? So this right here is our 5 factorial. Right? So this, I would say, is the multiplication principle. How does that work in terms of the formula? So I'll have 5 total objects, and I'm picking 5 at a time. Okay, but I'm picking them in random order. So this becomes 5 factorial divided by 5 minus 5 factorial, which is equal to 5 factorial divided by 0 factorial, which is 5 factorial divided by 1, because 0 factorial is defined to be 1, which is really just 5 factorial. All right? What if we said that I wanted all the shirts together and all the pants together? Okay? So all shirts together, all pants together. Right. The general formula for using combinations, and there's a formula for that, we'll see in a different video, but the general formula for combinations and permutations aren't really that hard to use, although doing them by hand and calculating the factorials would be pretty painful. The biggest issue in terms of solving combinatoric problems is that sometimes you have to have clever ways of thinking about the problem. And that's what we're doing here. So what do I have here? I could have all the shirts together, followed by all the pants together, or I could reverse these. So let's look at this. So what would happen? Well, I could have shirts A, B, and C in this order, and then pants X and Y, but I also could have A, B, and C and Y, X. But I could have A, C, B and X, Y, and A, C, B and Y, X, right? And I could have B, A, C, and with X, Y, and B, A, C, Y, X, and so forth. So what do we have here? Well, for each of the 6 permutations of shirts, right? Permutations of shirts. Is equal to what? Well, I'm choosing all of those, so it's really 3 factorial. 3 times 2 times 1, because I have 3 possibilities for the left one. That leaves 2 possibilities for the middle and only 1 thing for the right. That's 3 factorial equals 6. For each of those 6, I have my different arrangements of pants. And so we have permutations of pants. Pants is 2 factorial, which is 2. So I have the 6 times 2 equals 12. So we see there's 2 here, 2 here. There's 2, so there's really 4 for having shirt A for the left. Then there'd be 4 for shirt B for the left side. Then 4 for the other one. So 4 plus 4 plus 4 is the 12. That's if I do this. But we could have swapped them, right? So really, we could do all the same things for pants and shirts. So really we have 2 times this. But don't just think of it as being 2 times this. How many different ways are there to arrange these? Well, that's 2 factorial. So it becomes overall 2 factorial for the number of arrangements of either shirts on the left or pants on the left times the number of permutations of shirts times the number of permutations of pants, which would be 24. Or if we throw in something like, I also had suits. This will make it more clear why I didn't just say 2 times the 12. I said 2 factorial times 12 because there's 6 different ways to arrange this, right? Shirts, pants, suits, shirts, suits, pants, pants, shirts, suits, pants, suits, shirts, and finally suits on the left, and then the other 2 for the thing. So that would be the 6 factorial for that. Plus times what you would add into these as well. Okay? So like I said, you have to be sort of clever in how you think of the problem. And that, to me, is the biggest hindrance in solving combinatorics problems. The general idea, hopefully, especially if you think about it in terms of decision trees, like if you think about this, you could say 1, 2, 3, 4, 5. I could have shirt A here, shirt B, shirt C, pants X, pants Y. And if I choose A for the leftmost item, then I have 4 things to choose from. And then for whatever I choose here, I have 3 things. Well, it ends up with the 5 times each of those has 4, each of those has 3. That's still the 5 factorial. So that's permutations. And like I said in another video, we'll talk about combinations. And basically what we have to do there is we just have to remove the duplicates, because if we look at these 6 different arrangements, we said, well, these are considered the same. So I'm actually double counting, right? This was 6 divided by 2 was 3. I double count in this sense because there was only 2 possibilities. But I count multiple arrangements more than one time, or some different arrangements are multiple counted. And that's the biggest problem between combinations and permutations.